What chapters did we have for this weekend? 11 and 12? So 11 had high success. So maybe number 4 or number 6. And number 5. Number 3. Let's do number 3. Number 3. So number 4 and number 3. Let's do number 6 and then number 3. Okay, according to a publication, 13.8% of 18 to 25-year-olds were users of marijuana in 2000. A recent poll, 1346, selected 18 to 25-year-olds revealed that 223 currently use marijuana. At the 20% significance level, do the data provide sufficient evidence to include the percentage who use marijuana has changed from the 2000 percentage? Use the 1 proportion Z test to perform the appropriate hypothesis test after checking the conditions for the procedure. Okay, so we have what we're expecting for the proportion and what we sampled for the proportion. So if we want to test whether it's different from the 2000, then what will our hypothesized proportion be?
0.138.
Right. So the expected will be what we're hypothesizing. What we're saying if we don't reject the null, we're saying that things haven't changed. Right. Things haven't changed. So we're comparing to 0.138. All right. And then it says we just want to use it to perform that. Has it changed? Has it changed? So are we going to do less than, greater than, or not equal to? Just if it has it's changed, right? Has it changed or not from the 0.138. Question so far? Okay, the test statistic. So the test statistic is going to be for our proportion, right? Test, and that was that ugly thing, so we use StatCrunch to do this, right? So let's open up StatCrunch, and Oh, right. Thank you. They used to, I forgot about that. They used to have a little icon in iOS, and I didn't see it, so good. Thank you. Helps. Okay, so what are we doing? We are doing a proportion stats, right? One sample? Or z-test, was it? Where was this? Goodness of fit, right. Forgot. Chi-square, goodness of fit. No, that was the next chapter. This is proportion. This is proportion. This is with the summary, right? We just have the summary. This proportion, right? So number of successes was, in the sample, 223 out of 1346. And we've already done this. This is going to be our hypothesis test. It's going to be 0.138. And then P is different than 0.138. So I think that's everything we need. So compute, and it gives us the test statistic, which is 2.9439. Okay, 2.94. So what was the sample? So from the sample, we got the proportion to be 0.166, right? Which we're comparing to the 1.138. And our test statistic is 2.9439. So round to 2 decimal places. 2.94? Okay, the critical value. So the critical value is going to come from our 20% significance level. So 20% significance, we haven't really seen that before. What does that mean if we're doing a hypothesis test of just being different, right? Just being different means it's a two-tailed test. So how much area do we have on either tail? What's that? Right, which is 20. The 20% is the significance level. So 0.1. So you have 0.1 on the left tail, 0.1 on the right tail, and so we need z. So it's like minus z and z. Okay, anyone got a z chart? So this is an area, right? And we're back calculating what the critical value is. So everyone do that. So where are you going to look in your table? At what number are you going to look in your table? Are you going to look at 0.1?
Yes.
You could, or you could look at, what else could you look at?
0.90.
0.9, right? So if you wanted the positive z, you'd be looking at 0.9, all this area to the left of z, such that the right is 0.1. But if you looked at 0.1, you're going to get this value, which is
-1.28.
so plus or minus z of alpha over 2 is plus or minus 1.28. You need 3 decimal places. Can you get one more decimal place out of that?
I mean, on the z-chart is saying 0.1.
Oh, right. Okay, that's right. Z-charts only gives you. But is there an area that's exactly 0.1000?
No.
So which two are you comparing? 0.100 what and
Well, it's doing actually 0.1003.
1003 and
1.28.
okay. 0. There should only be four values. 0.09, 0.9 what? 89 what?
No, on the T chart it says the Z value for 0.1 is 1.282.
Oh, for 20%? On each side?
I'm just going off of
Yeah, I understand. So at the bottom of the Z chart, or the T chart, there's those Z values for those exact values of alpha. Right. So let's just try, what is this? So we want the Z, the plus or minus, right? Let's just try 1.28 and see if it likes it or not.
redo.
Right. All right, 1280, but maybe not. Oh, no, that was good. So just the value from the C chart is enough. And maybe they gave you some tolerance there. Okay, and what's the conclusion? So 1.28 and what was our, and 2.94. So this is 1.28. So where is 2.94? Is it in the rejection region or non-rejection? Rejection. 2.94 is up here in the rejection region. Meaning what? Meaning there's evidence. Is there evidence or is there no evidence? Not enough evidence. There is evidence to suggest what?
It's changed.
It's changed. What? The marijuana use is different than it was before. There is significant evidence to suggest that marijuana use is different, higher, right? So we're going to reject HO. The data do provide evidence to conclude the percentage is different. Questions on this one?
You go through the series of buttons in StatCrunch that you used?
Yep, sure thing. It's just proportion. Where is it? There it is. So we're doing proportion stats, right? These are I went to stat, proportion, one sample with summary. And that's right where you need to be. Other questions on this one? Okay, so then on the other assignment, I think we wanted to do number 3. And this is our chi-squared goodness of fit, this one. Very good, okay. So it says a certain type of, let's see if I can make this better here. There we go. So a certain type of candy is reported to be distributed with color percentages. So like Skittles or M&Ms, probably M&Ms because there's brown, right? So there's some brown Skittles. Okay, so the number of each color around a bag of candy is shown below. Chi-square goodness of fit test to decide whether the color distribution differs from the reported distribution. So they've done studies, and by having certain percentages of the different colors in M&Ms, they increase or decrease their sales. This is true. I don't know if you've heard this, but by having the right percentages, so they want it. So they're producing bags of M&Ms. They're going to pull some off the line and check to make sure they're getting the right percentages, because this is a lot of money, right? This is a lot of money for this company. If the percentages of their colors are getting screwed up, then over time they're not going to get the sales of M&Ms that they want. So this is the. Is this the observed or expected? What is this?
Oh, you have to get the expected from the percentage.
Yeah, but which, let's see, the number of each color in a random bag of candy is also shown below. So this is expected. So the percentage is expected and frequency is observed, is what I'm reading there. Yeah, reported to be distributed with the color percentages. A random bag is the number of each. So this is the expected and observed is the second row. So we can do this without doing the table. So the null and alternative hypothesis, what's the null hypothesis going to be?
The color distribution is the same as that reported.
Right. Always our null hypothesis is something like being equal, right? Things being equal. Always. Every problem we've ever done. And so what we're testing with a goodness of fit test is if our observed distribution is the same as our expected distribution. So that's going to be this one. So it's not that the frequency is the same for each color. So I just explained that by having a little less brown and more, or no, actually it's more brown or something, but more of certain colors and less of certain colors is what they want. So it's not that we want the frequency to be the same, but just that the overall distribution is the same as in our sample. Okay. So the test statistic, when we get that from StatCrunch, and this is this value that compares the observed of expected in each category and comes up with this one number that's indicative of how close the observed results are to the expected results. And there it is. All nice for us there. So we'll go to stat and go to goodness of fit, chi-square. So the observed was frequency. And the expected was percentage. And we do not want this. We have different percentages for each. Okay? And so I think it knows automatically if it's frequency or percent and automatically compensates for that. So if these numbers don't add up to 100, then it knows it's not percent, and it automatically takes care of it for you. So our statistic is 10.2609. Where is it? There it is. 10.26, 3 decimal places. What did I say? 02. 10 point. I forgot already. 10.261. 261. No. Here. 10.261. Okay. Got it. All right, and the critical value is going to come from our alpha 0.05. And how do we get the critical value? Okay, so we're using the chi-squared chart. Remember what kind of distribution is that?
Two-tail.
Two-tail? Chi-square? No, chi-square looks like this, remember? It's the special right-skewed distribution that looks like this. And so our chi-square was 10.26, and we want what? We want critical value for alpha 0.05 with how many degrees of freedom? 1, 2, 3, 4, 5, 6. One less than the number of categories. 11.07. You got that? You got that too, Gina?
70.
Yeah? Okay, so at the 5% significance level, our critical value is 11.07. What was our test statistic?
10.261.
Okay, is it in the reject or the non-reject region? Non-reject. At the 5% significance level. So here we are. Remember, the bigger that number is it that the distributions are more different or less different when that number gets bigger? The chi-squared number. That number gets bigger and bigger. Then are these distributions more different or less different? And we should know that. I'm glad I asked. What? If that number is bigger, Are those distributions more different or less different? What does the rejection mean? What does rejection region mean versus non-rejection? So bigger, chi-squared bigger means more likely to reject, right? You're going this way. You're more likely to reject. Are these more different or less different? More different, right? More different. That's the whole point. Because this is some sum of what? Observed minus expected. It's the sum of differences, right? The bigger those differences is, the bigger this number is, and the more different, right? So the more different, the more the sum of the differences will be more likely to reject, and the distributions are different. So here we are at 10.26. We're not going to reject. 3 decimal places.
11.070.
Okay. Good. And conclusion. Do the data provide sufficient evidence to conclude that the distribution differs from what they want? Yes or no? No, right? We're in the non-reject region. This number is too small to say at the 5% significance level that there's evidence of them being different. So there's no, because not sufficient evidence. And this will always be true. When we don't reject the null, it's because there's not sufficient evidence. That's always true. And when we do reject the null, it's always because there is evidence of disparity or difference. Okay, questions on this example? Okay, I hope that helped going through those. Okay, so the next topic that we have also uses a chi-square test, but to test something different. Okay, so let's talk about that. Okay, so the chi-square test can also be used to check the independence of two variables. So when we say independence, we're comparing two different variables. For association. So association means dependence. Cover your head. Okay, non-associated variables are called independent. And what does that mean? It means the outcome of one of the variables does not have influence on the outcome of the other. That's what independence is. The outcome of one variable does not have influence on the outcome of the other. So if they're dependent and they're associated, knowing what one is will influence what the other would be. Independent means if you knew what the value of one variable was, it would not have influence on the other. Okay, so let's do some examples. So year in school and hair color. Are those associated, dependent, or non-associated, independent? Year in school and hair color. What would you say? Independent. If you knew someone's hair color, it would have no indication on what year in school they were. Okay, what about year in school and number of hours completed? Year in school and number of hours completed. Would this be associated, dependent, or independent? Right. So if someone had, 110 hours completed of school, what happens to their probability of being a freshman? Goes way down, right? If you knew how many hours someone had completed, that would be indicative of somewhat indicative of what year in school they would be. Okay, so this is what we're talking about. So we can use the chi-square test. Now those were very exaggerated examples. Okay, so there's lots of data in life where it's not. You look at the data, you're like, I don't know, is there an influence or not? Okay, and just like all the other tests we've done, it's a matter of to what degree of certainty do you want to be, right? So it's like you have to pick a significance level, and because it's a gray, right? It's a gray area. So at a particular significance level, we're going to look at two variables and say, is knowing one, does it help you know the other or not? That's what this is about. So first example here is it substance day, right? Marijuana and now drinks per month. Contingency table of marital status and alcohol consumption for 772 randomly selected U.S. adults. Okay, so what are the variables? The first variable is marital status. Single, married, widowed, divorced. Right? That's a variable. Go from person to person, it changes, right? Drinks per month is another variable, and they've got 3 categories. Don't drink, 1 to 60 per month, over 60 per month. Okay, so let's look at this here. So if these were independent, so let's look at just the total. Let's look at the totals of the different marital status categories. So how would we get, what percentage of people are single according to this sample? What percentage? How would we get the percentage of people that are single? Yeah, so we're going to do 354 divided by 1772. So we're going to get these percentages of marital status. Everyone do one, all right? So some people do divorce, some people do widowed, some people do married, and we're going to get these values. As soon as you get one, shout it out.
Divorced, I got 0.058.
0.58. 5.8%. Another one, shout it out.
0.081 for widowed.
0.081. Okay?
0.19, how many decimals is this? 3?
Sure.
So 0.120 technically, if you round, for single.
0.1.
It's 0.1997.
So 0.200.
Yeah.
200.
Okay, very good. And who did married? 662. So here's how this works. So these are the percentages. 20%, 66.2% married, 8.1% divorced, or widowed, I'm sorry, and 5.8% divorced. So here's the deal. If they were not, and so now, here's the total number of people that abstain. If these aren't associated, then what percentage of this 590 would you expect to be single if they're not associated? What percentage of the 590 who abstained would you expect to be single if they're not associated variables? 20%, right? So since 20% of all the people sampled were single, then if they're not associated, then you'd expect that 20% of the 590 would be single. And if they're not associated, then what percent would you expect the married of the 590 to be? You'd expect 66.2%, right? So if they're not associated, then there's no influence on there's no influence of marital status on drinks per month. So we'd expect 20%, 66.2%, 8.1%, and 5.8%. So what is 20% of 590? 117.9. So if in each category of drinks per month we're going to have the same percentages, that's what we would expect if the variables are not associated. Okay, so married, we want what? 66.2% of 590. Should get 390.6. Is that what you got? And what's 8.1% of 590? $47.6? And then 5.8% of 590. Okay, and then we would do that with the same thing with every column, right? So the second value in each box is if they weren't associated, if they weren't dependent, we'd expect these exact same percentages in each of these drinks categories. Then there'd be no association. There would be no indication that, given that somebody drinks 1 to 60 per month, you'd have no way of knowing that there'd be no indication or more likelihood of any of these, because it's the same as just your overall percentages of marital status. So all those second numbers in each box would be what would we expect if the variables have no influence on each other. So we're going to get our chi-squared statistic is going to be the same thing again. It's going to be observed minus expected squared for each one, and then sum them up and divide it by expected. Okay, does the idea make sense? What we're doing here? Okay. All right, so here's some assumptions that have to be in place. Okay, so all expected frequencies are 1 or greater, so those are the values inside the box. Okay, and most 20% of the expected frequencies are less than 5, so 4 or less. So if you have too many frequencies, like in our chart, that are too low, then this is not reliable. And we have a simple random sample. Okay? And so then our null hypothesis will always be the two variables are not associated. Is that independent or dependent?
Independent.
That's independent. And then the alternative would be, no, there is influence. Knowing one will help you know the other, right? Knowing the value of one variable would help you know the other. Okay, we've got a significance level, and we have the same chi-squared, but now it's going to be all those differences squared over E. So like we saw in that table, observed minus expected. I think we have 12 of those. We had 12 values in the table, 4 by 3. So you have 12 things you're adding up. So this is sum, right? You're adding up 12 differences squared over E. And that will give you chi-squared. But we're going to use StatCrunch, okay? But you should know what's going on. Yeah?
You explain number 2 of the assumptions again?
So we had 12. There were 12. So what is 20% of 12? There were 12. So do 20% of 12. So 0.2. So 2.4. That would mean that you could have 2 of these that had a frequency, an actual observed frequency of 4 or less. But if you had 3 of these, if you exceed that 20%, if there were 3 in here, then the test would not be reliable. Does that make sense? So we could have 0, 1, or 2 of these boxes being 4 or less in their frequency, then we're okay. But if 3 or more of these boxes showed less than 5 observations, then you can't really do the test reliably. Does that answer it?
Yeah.
Cool. So let's look at, and so it's going to be chi-squared test. So it's going to be the same thing you did for goodness of fit. You're going to have the test statistic, and you're going to have the critical value, and you're going to have a p-value. And so everything else is the same after you get the test statistic and the critical value. Oh, here's the new thing though, degrees of freedom. Degrees of freedom is similar to goodness of fit. You take 1 less than the first variable, so I'll say v1, and you take 1 less than the second variable, number of categories, and then you multiply. Number of what? Yeah, it's called categories. So what would the degrees of freedom be for the example that I showed back here? This one. What would the degrees of freedom be?
68 times 4 is 10.
So how many categories here? 4. Subtract 1. How many categories here?
3.
Subtract 1. So it'd be 3 times 2, or 6 degrees of freedom for this chi-square test. 1 less than each, and then multiply. Okay, so I don't know if this is maybe before most of your time, but there was the original movie reviewers were Siskel and Ebert. Siskel and Ebert were the original movie viewers, and so when I was growing up, it was on PBS, and these guys were fighting, duking it out over whether movies were good or not. Okay, now there's movie reviewers everywhere, and no one's really famous. But these were the 2 original, Gene Siskel and Roger Ebert. And so, is there association? We're asking the question: is there association between Siskel's reviews and Ebert, or Siskel's ratings and Ebert's ratings? Okay, so is there association between? So if you knew, so basically we're saying if you knew what Siskel rated a movie at, would that give you a clue as to maybe what Ebert's rating was, or not? And what would you guess? Yes or no? So do you think, so is there some is there some degree of agreement between them, right? So it was great when they disagreed, right? So he said thumbs up, he said thumbs down, and then they would argue, right? This is a great movie. No, this sucked, so okay. And so, but is there some degree of agreement? Like if Roger Ebert gave it thumbs up, would that kind of maybe give you some indication that Siskel would always also say thumbs up or not thumbs down? So that's what we're testing for. That's what we're testing for. Okay. So we've got how many degrees of freedom? 4, because it'd be 2, 1 less, and 1 less, so 2 times 2. And so we're actually going to put this data into StatCrunch. In that, just like that, in that table. Are the numbers big enough there? Can you read that? Okay, there we go. All right, so we're actually going to put these tables in. So I'll use 5, 6, and 7. So and we can just type in what 24, 8, 13, and then 8, 13, 11, and 10, 9, 64. Okay, you don't have to put the totals in. It'll do that for you. Okay, so we're using variables 5, 6, and 7, rows 1, 2, and 3. And so we're going to go to stat, and we're going to go to tables, contingency with data. So contingent. So we have a table of data, and contingency means contingent, dependent, right? Is one dependent on the other? Contingency, again, contingency, contingent means dependent, but we want summary, not data. Okay, there we go. So now we're going to select columns 5 through 7. We want expected count for display, and then we want the chi-square test for independence. Oh, for goodness sakes. I don't think it matters. Get that. I don't understand what they mean by row labels. Okay, so here's that table that we were talking about. So we'll review that again. But here's that table, 24, 8, 13. And so then in parentheses would be the expected that we did that before, right? If there was no influence at all, then these would be the expected counts. Okay, and so what is our value? 45.3. So 4 degrees of freedom, that agrees, right? 2 times 2, and then 45.3 is our test statistic. So we need a significance level. So let's do 5% significance. So what was the test statistic again? 45.35. And let's say our alpha, let's do 5%. And our degrees of freedom are 4. So with that, we can get the critical value. So our critical value is, for chi-square, 5% significance level, 4 degrees of freedom,
9.488.
9.49. Okay, and so then what area is here? How much area under the curve is that? 5% of the curves, that's our 0.05. And are we, based on the independence test, are we in the non-reject or the rejection region?
Rejection region.
Way out here. Way out there. So, and what's that p-value? The p-value was over here. Very, very small, less than 0.0001. The actual area to the right of our statistic, test statistic, is 0.000, less than that. So what is the data indicating here? But we're testing for independence or dependence on Siskel's ratings versus Ebert's ratings. So what is this indicating? Independence. Totally, there's no dependence of one on the other. Agree?
We reject the null hypothesis.
And what was that null hypothesis again? They're not associated.
So would it be that we will not reject the null hypothesis because there's not sufficient?
Well, you guys are all over the place. Where's the rejection region? Right or left?
Right.
Reject. Non-reject. Okay, and what was the null hypothesis? we never really formal about it, but that it's always, so this is null would have been that they do have association or not non-association. No association of ratings. There is an association of the ratings, meaning if you knew one, you have some kind of indication of what the other would say. So what does this huge chi-squared statistic tell us?
You reject them all because there's sufficient evidence to say that they're associated.
Okay, so before we were saying non-associated. So does this mean associated? Strong suggestion of association or non-association? Which? Look, the null hypothesis is no association. This is the non-rejection region, meaning we don't reject the null. The rejection region's out here. So we reject it in favor of the alternative. So if we're way, way out here, which is it? An indication of no association or there is an association? There is, right? A very strong indication. If one says thumbs up, then there's probably a really good likelihood that the other is definitely not going to say thumbs down and probably also said thumbs up. Okay? So, yes, there is a strong degree of agreement between them. Even though they did disagree on some movies, this is saying that there is a significant degree of agreement or association, dependence on the ratings at a very low p-value, meaning there's a very low chance we made a type 1 error that we're rejecting when we shouldn't have. Very low chance that we would reject when they're actually not associated. So it's like almost nil. Okay, does it make sense? Anybody have a question? Okay, so can you even, it's a little fuzzy. Can you read it? Make it bigger. Okay, so learning at home. So the two variables here were social class, and then what the student's social class were, and then their knowledge of nursery rhymes. Okay, so we're asking, is there an association between what's the difference between middle class and working class? Don't middle class people work?
Yeah, we do.
Right? Is this like, is this in some countries, is this like working is like a lower class than middle class? Is that the
I
indicator?
think so. Sometimes the middle class in places can be like the merchant class.
Oh, so like business owners? So they, right, got it. Okay. So then working would be like laborers. Okay.
Yeah, white collar, blue collar workers.
What's that?
Maybe the middle class is a stay-at-home mom and the working class.
Something like that. Okay. All right. So they looked at those two classes and then also what the children's nursery rhyme knowledge was, or maybe it's, 66 children in kindergarten through second grade. Okay. So is there some correlation between or association between the two? So what would our null hypothesis be? No association, right? Independent. The null hypothesis is always going to be no association, independent. And then the alternative would be knowing social status would give you some kind of information. It would help you guess more what the nursery knowledge was of the children. Dependence of the variables. So now what were our assumptions, right? Our assumptions were that we have no frequencies, every frequency of at least one, And then the next one was that 20% of the frequencies are, at most 20%, are less than 5. So how many of these are less than 5? No, less than 5. How many? There's one that's less than 5. Okay. What percentage of all of the possibilities is that? So what percentage? So how many possibilities do we have? 6. So what is 1/6? That needs to be less than 20%. What is 1/6? 16.7%. So are the assumptions met?
Yes.
Yeah, because only one is less, or I'm sorry, less than 20% of them are less than 5, right? One of them is less than 5, that's 16.7%. And it's only one of them. So we're good, the test should be reliable. Okay, so we want to find then I want to use, are assumptions 1 and 2 satisfied for the chi-squared independence test? Yes, we just checked that. We want to use alpha as 0.01, and we want to do the chi-squared test with alpha at 0.01. So let's do the critical value first. You guys can do that. So while I'm getting StatCrunch ready, you're going to find the critical value. You've got 2 and 3, right? Two categories on the one variable, 3 categories on the other variable, and we want to find the degrees of freedom. And then you have a 0.01 significance level. So from that, you're going to find your critical value. And talk amongst yourself. Make sure you agree. Okay. Okay, so since I blew this so bad, we're gonna go through this again. So here we go. Did you guys agree on the critical value? Everyone in agreement? Okay, so I'm gonna use 5, 6, and 7 again, and middle class. So it's 4. You put the summary categories in 13, 15, and then 5, 11, and 18. Okay, so here's what we want. We want stat tables. Okay, so we made a table. So we want tables. Contingency. Contingency means dependence. Summary. So we have a summary of all 6 categories. How many fit in each category? All right, then we're going to choose the columns where the data is. So it's 5 through 7. So you got to select all of them. Okay. Row labels. I'm just going to put variable 5 row labels. I'm not really sure what that is. And then we want expected count, right? That's going to be our parentheses. It's going to tell us what we would expect in each one to display those. And then we want a chi-square test for independence. And then we're going to compute, and we're going to compare it. We're going to get the chi-square. So look at these, before we actually do it here, look at these expected values. So we had 4, we expect 4.36. 13, 11.64. 15, expect 16. So it looks like if we just had to guess, maybe they're not associated, right? Maybe. But what's...
It says warning, over 20% of the cells have an expected count less than 5.
Huh?
Under the
I know, but that's not true.
I think it's because you only selected one of the rows, maybe?
Or maybe it's counting on the far left, it says 4 and 5. Maybe it's counting that for it. For whatever reason. Oh, it's because the expected count is less than 5. you know how it's 4.36 and 4.64?
Yeah.
Wouldn't that be greater than 20%?
Expected.
Yeah, I think that's what
Expected. Let's see here. Ah, it's not observed, so it's expected. Okay, we were looking at observed frequencies, but it's expected frequencies. So good. Let's go back. So it's about whether the expected frequencies are less than 5, not the observed. So because we have 2 of them, that's what, 33%. 33% of the cells have an expected frequency less than 5. And they're saying warning. So this means that the test is not necessarily reliable. So it still gives you look, it still gives you a value, it still gives you a chi-squared value, it still will run the numbers, but there's indication that the test might not be accurate. What did you get for a critical value?
9.210.
All right, so here's the deal. Because the critical value and the test statistic are so far different, it's probably okay that we've got two that are less than 5. Two of the cells that are less than 5. If they were really close, so if the test statistics was really close to the critical value and we're making a decision right there at the borderline, then we would probably say this isn't good. But our critical value is like 0.49. Our test statistic, and what was our critical value?
9.210.
All right, so even that we have one too many categories that are less than 5 expected categories. Look how different those are. Pretty different, and probably still safe to conclude what? Reject or do not reject the null. Do not reject, and that's because what?
There's no association. They're independent.
Right, there seems to be no association between, or no dependence between social status and nursery rhyme knowledge. So it's just a warning, and then they still give you the data, and because those are so far different, you know, we can pretty much still conclude and reject the null, and don't reject the null. And there is evidence or there's not evidence. There is evidence or there's not sufficient evidence. There's not sufficient evidence to say that socioeconomic status socioeconomic status is a determinant or has influence on whether the children know the nursery rhymes or not. Yeah.
So did we find 0.49 to test against 9.2, or is it?
It's the same thing we've always done. So this is our test statistic. That's the chi-squared test statistic, and you compare it against your critical value. Make sure you reject and your non-reject, just like before. And so that 0.49 is way over here in the non-rejection region. You see it? Okay.